Welcome. Today we're going to talk about one of the four basic types of tissues in the body, connective tissue. Connective tissue is the most abundant type of tissue in the body, and it's so important because of its ability to join and support structures. So sit back, relax, and enjoy your closer look at connective tissue. So let's talk a little bit about connective tissue. So first we said it is the most abundant type of tissue in the body, but let's get a little bit more specific. So connective tissue is tissue where the cells are distributed within an intercellular or extracellular matrix, and we often abbreviate extracellular matrix as ECM. The extracellular matrix is any part of an organism's tissue that is located outside of the cell. So when we look at that and look at a picture, here is a cell and here is a cell, and notice that they're not touching one another, and that happens a lot in connective tissue. That's different than epithelial tissue. And in between those cells we have a bunch of fluid, and in that fluid we see these purple string-like structures. We see some things that are called protoglycans. So we have some interesting stuff in this extracellular matrix that we'll talk more about in a second. So the extracellular matrix is an important aspect of the cells. So what falls under this connective tissue? So first we have cartilage, that's a type of connective tissue. We have bone, bone is a type of connective tissue, and we also have blood. And we're going to talk about each one of those kind of individually so that it will give you a better understanding of what connective tissue is. So let's move on now to what are the general characteristics of connective tissue. So let's talk about the general characteristics of our connective tissue. So first we did say that it was the most abundant, so that's an important aspect to remember. But let's talk about all the different jobs that it does in the cell. So first thing is it supports and protects, and that's really important. We need to have that in our body to make sure that our organs are protected, among other things. Next, it helps to fill space because not all of our cells are touching one another. And so because of that, we need to have something that is filling the space between them. We have fat storage. And lastly, we have production of blood cells, which is really important. Red blood cells do a lot in our body. We'll talk more about that when we talk about bone. And lastly, it provides a framework for structure in our body besides our bones. And then a couple of other important characteristics are that we have, it is a vascular tissue, and that means that it has a good blood supply. It has a dedicated blood supply. We actually have different capillaries and blood vessels that are bringing blood to this type of tissue. That's different than epithelial tissue. And then lastly, cells usually divide. So, and that's also important. This tissue is often injured. Say you get a paper cut or a burn, you can actually damage your connective tissue, and if you didn't have a way to replace that tissue, we'd be in big trouble. So cell regeneration, or the fact that the cells can divide in this layer just like epithelial tissue, is a pretty important aspect of connective tissue.
Good afternoon, Hobbytown, USA, Lee speaking.
3 years ago, Lee Spivak sliced off the tip of his finger in the propeller of a hobby shop airplane.
I was behind the wing, and I went like this. And
What happened next propelled him into the future of medicine. Spivak's brother Alan, a research scientist, sent him this special powder and told him to sprinkle it on the wound.
And I powdered it on until it was covered.
To his astonishment, every bit of his fingertip grew back.
Your finger grew back flesh, blood, vessels, and nail
4 weeks.
in 4 weeks.
Right.
Is this essentially what regrew Mr. Spivak's finger?
Yes, it is. We took this, turned it into a powdered form.
Dr. Stephen Badalik of the University of Pittsburgh says that powder, a substance made from pig bladders called extracellular matrix, holds some of the secrets behind the emerging new science of regenerative medicine.
It tells the body, start that process of tissue regrowth.
Badalik, the lead researcher at Pittsburgh's McGowan Institute for Regenerative Medicine, is one of the many scientists who now believe every tissue in the body has cells which are capable of regeneration. All scientists have to do is find enough of those cells and direct them to grow. Somehow the matrix summons the cells and tells them what to do.
It first gets them to the site where they need to be, but then it helps instruct them in terms of where they need to go, how they need to differentiate. Should I become a blood vessel? Should it become a nerve, a muscle cell, whatever?
If this helps Mr. Spivak's finger regrow, Could you grow a whole limb?
In theory.
Here you see a engineered blood vessel.
But there are advances in the science of regeneration that already go beyond theory.
You can actually see the vessel beating.
In this lab at Wake Forest University, a lab he calls a medical factory, Dr. Anthony Atala is growing body parts.
That's a heart valve.
This is an engineered heart valve.
Atala and his team have built from the cell level up 18 different types of tissue so far, including muscle tissue, whole organs, and the pulsing heart valve of a sheep.
And is it growing?
Absolutely. These cells are continuing to form new heart valve tissue. When people ask me, what do? We grow tissues and organs.
You really are making body parts.
We are making body parts that we can implant right back into patients.
Dr. Atala, one of the pioneers in regenerative medicine, also believes every type of tissue has cells ready to regenerate if only researchers can prod them into action. Sometimes that prodding looks like science fiction.
You're using heart cells in an inkjet printer.
Yes.
What's emerging from this printer is the heart of a mouse. Mouse heart cells go into the ink cartridge and are then sprayed down in a mouse heart pattern, layer by layer. Dr. Atala believes it's a matter of time before someone grows a human heart.
The cells have all the genetic information necessary to make new tissue. That's what you're programmed to do. So your heart cell is programmed to make more heart tissue. Your bladder cells are programmed to make more bladder cells.
Atala's work with human bladder cells has pushed regenerative medicine to a transformational breakthrough. In this clinical trial at Thomas Jefferson Hospital in Philadelphia, Dr. Patrick Chenot is performing a bladder transplant with an organ built from the patient's own cells. In a process developed by Dr. Atala, the cells were grown in a lab and then seated on this bladder-shaped scaffold. 8 weeks later, the scaffold, now infused with millions of bladder cells, is transplanted into the patient. When it dissolves, Dr. Chenot says what's left will be a functioning new organ.
The cells will differentiate into the two major cells in the bladder wall, the muscle cells and the lining cells.
They know to do that themselves.
They do.
Are you thinking this is the future?
It's very much the future, but it's today. We're doing this today.
1, 2, 3, look! Today, one of the biggest believers in regeneration is the United States military, which is especially interested in the matrix that regrew Lee Spivak's finger. The Army, working in conjunction with the University of Pittsburgh, is about to use that matrix on the amputated fingers of soldiers home from the war.
Can we make skin? Can we make bone?
Dr. Stephen Wolf at the Army Institute of Surgical Research says the military has invested tens of millions of dollars in regeneration, hoping to regrow limbs, lost muscle, burned skin.
And you see these casualties coming back, and it's hard to ignore that this guy is missing half his skin. This guy is missing his leg. You start asking the question, is there somebody out there who may have some technology that can do this for us?
You mean regrow the tissue?
The answer is maybe.
At the burn unit here at the Brooke Army Medical Center, the very idea of regeneration brings a glimmer of hope.
This arm burnt off, all the skin and muscle.
Army Staff Sergeant Robert Henline was the only survivor of an IED attack on his Humvee north of Baghdad.
Well, what do you make of the fact that the Army is so heavily invested in that technology?
It's a great idea that we can come up with something that's less painful and can heal it with natural growth without scarring on it. Definitely something to check into.
The race to check into regeneration has gone global. This machine, being tested in Germany, sprays a patient's own cells onto a burn, signaling the skin not to form scar, but to regrow.
You could fashion this into a tube like this.
In a clinical trial in Argentina, Dr. Badalik is about to implant matrix material, shaped like an esophagus, into patients with throat cancer.
You expect the body to regrow a piece of its esophagus.
We fully expect that this material will be degraded and cause the body to reform normal esophageal tissue.
Inducting one?
And in this clinical trial at the University of Pittsburgh Medical Center, patient Mary Beth Babbo is getting her own adult stem cells injected into her heart. The hope is to grow new arteries. Her surgeon is Dr. June Lee.
It's actually, if you will, what we would consider the holy grail of our field for coronary artery disease.
The holy grail because a patient who can regrow a blocked artery may never need surgery.
It's a big difference from open heart surgery to this. If people don't have to go through that, this would be the way to go if it works.
Corporate America already believes regeneration will work. Investment capital has been pouring in to commercialize and mass-produce custom-made body parts.
We're actually building a very real business around a very real and compelling patient need.
Dr. Stephen Nichtberger is the CEO of the Tengion Corporation, which has bought the license, built the factory, and is already manufacturing the bladders developed at Wake Forest University we told you about earlier. Tengion believes regeneration will soon revolutionize transplant medicine. Transplant patients, instead of waiting years for a donated organ, will ship cells off to a lab, wait a few weeks, and grow their own.
I look at the patients who are on the wait list for transplant. I look at the opportunity we have to build bladders, to build vessels, to build kidneys. In regenerative medicine, I think it is similar to the semiconductor industry of the 1980s. You don't know where it's going to go, but you know it's big.
Alright, so now that we really understand the extracellular matrix, let's talk about the types of cells we find in connective tissue. So first off, we have fibroblasts, and fibroblasts are a really cool cell. They're the most common type of connective tissue cell, and they're large and they're star-shaped. So let's add that. So we have large, abundant, and star-shaped. Okay, these star-shaped cells produce all the protein fibers that allow connective tissue to do their job of kind of supporting and creating framework. And we'll discuss the types of protein fibers in depth very shortly. The second type of connective tissue cell we have are the macrophages. And the macrophages are wandering cells, which means they wander around the body, and they're phagocytic, which means that they engulf particles that are not part of your body. So they are always on the lookout to seek and destroy bacterial cells or viral cells. So they're really important for fighting infection and immunity. And we're going to watch a brief clip here in a second that further explains those important cells. And then the last type of connective tissue cells are mast cells. And mast cells are fixed, just like fibroblasts, and that means that they stay in one place in the extracellular matrix. They don't move around like the macrophages. And they release chemicals that are important in blood clotting and allergen response. So heparin is the chemical that they release that helps to prevent blood from clotting, and that helps your blood to move through your body as it should. And then they also secrete histamine, which promotes inflammation or when tissues get swollen. You've probably heard of antihistamine like Benadryl, which works to counteract inflammation. And histamine is a really large part of allergen response in the body. And so we're also going to watch another brief clip on allergen response. So we're going to watch two clips now, one on the macrophages and one on allergen response. So, as you saw, macrophages are pretty skilled at being able to capture bacteria and quickly dispose of them. Let's watch something on allergen response next.
An allergy is an overreaction of the immune system to a normally harmless substance called an allergen. Common allergens include pollen, animal dander, down feathers, mites, chemicals, and a variety of foods. On first exposure, the inhaled allergen enters the mucous membrane lining the nasal passages, where it is taken up by the antigen-presenting cell, which presents it to the T cells. These T cells activate the B cells to release substances called IgE antibodies against the allergen. These IgE antibodies sit on the surface of the mast cells. The mast cells have granules containing chemical mediators like histamine and prostaglandins, etc. On exposure, the allergen binds to the IgE antibodies present on the mast cells, cross-linking them. This results in the release of histamine, prostaglandins, and other mediators into the surrounding tissue. These mediators cause dilation of the surrounding blood vessels and increase their permeability. This results in the nasal stuffiness, sneezing, and mucus discharge of allergic rhinitis.
So, just to sum that up again, when your nose takes in allergens, those allergens bind to something on the surface of the mast cell. That causes the mast cell to release histamine, and that histamine causes a dilation of your blood vessels, which is what causes swelling or inflammation. And then that swelling in your nasal passages is what creates your stuffiness. Pretty cool, huh? Okay, so let's talk now about the different types of connective tissue fibers. There are 3 types of fibers found in connective tissue. They're all produced by the fibroblast cells in the ECM. And the fibroblasts, again, are those large star-shaped cells that are fixed in place. The first type of connective tissue fiber is collagen, and it's a protein that forms rope-like filaments with great strength and elasticity. And so you can think about it like how we make traditional rope. We have these groups of 3 strands of collagen that get wrapped around one another, and then thousands of these collagen fibers group together to form connective tissue, like tendons and ligaments. And then we also have elastin, and elastin is a different kind of connective tissue, and elastin is much more elastic and can stretch a lot more than collagen can, which you can see here by the shape of the protein fibers. They're much more wound up looking, like coiled springs almost, and that's because elastic is what gives us all of our elasticity in our connective tissue, or the pulling and the releasing in our tissues. So let's move on and let's talk more about collagen. So because collagen fibers are strong and also somewhat elastic, they're often used in cosmetic surgery through injection into the face and other areas of the body. Doing so reduces wrinkles and adds fullness, but it doesn't always work out as well as you might think. So I just wanted to show you some pictures of different actresses that have had collagen injections into their face. So you can see that while they might have less wrinkles, that their faces are a little swollen looking, and that's because, again, collagen does provide a significant amount of fullness to the face. So don't do it. Don't do cosmetic surgery. All right. We also have a bunch of diseases that can result if the collagen protein is not formed properly, if those 3 triple helices aren't wrapped correctly. And the first one is Marfan syndrome. And Marfan syndrome produces individuals that are tall in stature. So we can see this guy is very tall, really long limbs, and that might not be bad in and of itself, but there's also a heart condition, heart malformation that also comes with this particular disease. So a lot of people that are very tall are tested for Marfan syndrome when they're young because that heart condition needs to be fixed if they're to live a normal life. My mother, who is very tall, was actually tested for Marfan syndrome. We also have chondrosplasia, and chondrosplasia here you can see results in a malformation of hands and feet, and that's because the collagen chains are made too wide, so the rope would be made too wide. We also have osteogenesis imperfecta, otherwise known as brittle bone, and that's where we have issues with bones breaking more rapidly and with more frequency than they should. And then lastly, we have dystrophic epidermolysis bullosa. I don't think I said that right, but basically it's where the collagen breaks down underneath of the skin, and it doesn't allow the layer of the skin or epithelial tissue to attach properly to the connective tissue below, and it causes blistering and different redness and coloration differences in the skin. Okay, so we have talked about the extracellular matrix, we've talked about the cells that we find in connective tissue, and we've talked about the 2 fibers that we find in connective tissue. So next up, we'll talk about the categories of connective tissue.